Welcome back. It's time for video 5. This will be our final video for our study of Unit 1 in Math 109. So with no further ado, let me go ahead and share this PowerPoint and we'll continue our study on sequences. From there. So we're going to move right into example 5. We're back to recursion. Looks like we are given a first term of 4 and a recursive rule that says term a sub n plus 1 can be found by taking 2 times term a sub n. So as previously pointed out, the first term we know, and we'll somehow be using it, to create term 2. All right. So it's important for us to recognize if we want that little subscript n plus 1 to be worth 2, n has to be played by 1. That would mean term 2 becomes 2 times term 1. Term 1 happens to be 4, we know that. And you guessed it, that gets us term 2 at 8. All right, reminding that term 2 is 8. That second term will somehow create the third term. And again, for importance for us, that subscripting n plus 1 becomes a 3, has a value 3 if n is 2. And term 3 then becomes 2 times term 2. Term 2 was 8. You guessed it, that makes term 3 16. So those of you can see what's happening in every sense here. We're taking a term that we already know and in effect doubling it to create the very next term in our sequence, reminding us that term 3 was 16. For that little subscript to be worth a 4, n has to be worth 3. So that makes term 4 2 times term 3. You guessed it, that's 2 times 16. That makes term 4 32. We got one more to go, and we will have found term 5. So here we go, reminding us that term 4 was 32. And if that subscripting n plus 1 is to be worth a 5, n has to be played by 4. And all that means to you and I is that term 5 is in effect 2 times term 4, which we happen to already know was 32. That makes term 5 64. And there is term 5. And you guessed it, we have successfully found the first 5 terms of that geometric sequence in recursive form. All right, so in every case, we were doubling to get from term to term. Cool, cool, cool. All right, here's an nth term. We've contrasted previous recursion to nth term. It's very similar in terms of geometric versus arithmetic. If you want the first term, you put in 1 for n. If you want the second term, you put in 2 for n. So if we work through this thing, here we go. Plugging in 1 should get us the first term. And you guessed it, 2 to the first is 2 times 3 makes the first term 6. Unlike recursion, you will not be using that 6 to create term 2. You'll find term 2 by simply putting 2 in for n. All right, so 3 times 2 to the second, if you will. 2 to the second is 4, and 3 times 4 looks to be 12, and term 2 is a 12. Again, those of you who have good patterns of observation, you could now see a trend, and you could probably write some more terms pretty quickly, and we'll continue in this approach. If you want the third term, we'll put 3 in for n, and that makes us take 3 times 2 to the third. 2 to the third is 8. 3 times 8 is 24. Term 3 in play at 24. Finding term 4 puts 4 in for n. We're going to find 3 times 2 to the fourth. 2 to the fourth, 16. 16 times 3 at 48. One more term to go, if you will. So we'll put 5 in and we will find term 5. 2 to the fifth is 32. 32 times 3 looks like 96. Run them all in. 6, 12, 24, 48, 96. Looks like in every case we are doubling to get from term to term. So that's an example of an nth term sequence generation. Not too bad. All right, a word problem. Those of you who are, well, I'm showing my age because I'm old enough to remember the Muppet Show. And 2 of my favorite characters were Bunsen, Honeydew, and Beaker. All right, so here's the deal. Bunsen Honeydew starts a lab experiment, puts 2 bacteria in a petri dish. Beaker notes that the number of bacteria triples every hour. So the question is, how many bacteria will be in the petri dish after a fixed number of hours? Again, if you're really a high-tech algebra scholar, you can knock this thing out pretty fast. If you say, my head hurts, it's been a long lesson, Dale, I got you. So maybe what we could do is we could realize that there's 2 to start. And after 1 hour, according to the dude who wrote the problem, the number triples. So after 1 hour, there would be 6. After 2 hours, that 6 gets tripled and there are 18. After 3 hours, the 18 gets tripled and there are 54. After 4 hours, the 54 gets tripled and we're up to 162. After 5 hours, the 162 gets tripled and we have 486 bacteria in our Petri dish at the end of 5 hours. So that's cool. We just did part A. Nobody got hurt. 10 hours, just a bigger, painful kind of operation. You could just continue the way we've already done. In fact, you and I would be sophisticated, and we could take the number that was there after hour 5 and go to 6 and so on. I decided that we'd do a chart because charts are fun. So what I did is I basically took the information that we'd already incorporated up for the first 5 hours. All right, put time in there after a certain number of hours and how many bacteria were in the dish. And again, notice that in every case, as you move from 1 hour to the next hour, right, in effect from one column to the next column, the number of bacteria is tripling. So after 10 hours, you can see there's a pretty large number of bacteria in that Petri dish, 118,098. So I love the little chart. If you're a chart mechanism kind of person, it helps organize your calculations. That's pretty cool. Last but not least says, all right, take away the fixed numbers and put an N in there. And this is harder, I think, for a lot of folks. I realized that after 1 hour, it was just 2 times 3 to the first. After 2 hours, it was 2 times 3 squared. 3 squared actually was 9, and 2 times 9 was the 18. So if you're really locked into a pattern, you see that in every case, that exponent matches the number of hours that have passed since you and I putting 2 bacteria into the Petri dish. So after n hours, if we were to continue, it looks like whatever the number of hour is after the start, that becomes the power on that 3. And you guessed it, the formula would be 2 times 3 to the n. And that would be our answer to our last Bunsen, honeydew, and beaker problem. Congrats, you've survived all the way to the end of Unit 1's PowerPoint, where you are invited to begin work on your assignment 1C. Again, problems from the book, a few more this time. This section does have a math connection. You'll find ways for us to introduce the concepts and tie them into a broader math sense. So again, pull them down, scratch paper, notebook paper, loose leaf, unlined, whatever you like to work on, solve them out, crank them into PDFs and send them to me at that Dropbox, and you will have successfully completed assignment 1C. There are additional things for you to look at in this unit, and there is an assessment for the unit, basically a test on unit number 1 you'll get as you wrap up the work for unit number 1. That, my friends, wraps our PowerPoint sequence, our video sequence for unit 1. I'll be back in a bit with a sequence of videos for unit 2. We'll see you then.